Hello all, I'm Reet, and it is my pleasure to present our paper titled Vertex Reordering for Real-World Graphs and Applications and Empirical Evaluation. Let us start by looking at what vertex reordering is. Given a graph G with vertex set V and edge set E, then the vertex reordering pi of V becomes a one-to-one mapping of the vertices to any linear order of 1 to n. The objective of reordering is to preserve the neighborhood properties of a graph. We formalize this neighborhood property by gap measures. What are they? So the first one is average gap profile of a given ordering for an input graph, which is the average linear arrangement gap, or the absolute difference between the rank of two vertices which have an edge between them or adjacent to each other, and then we average it out over the whole, all the edges in the graph. The second one is the graph bandwidth, which is for any two pair of vertices I and j in the graph such that they're adjacent to each other, the maximum separation between their ranks in the vertex array. Part of our objective is to compare a representative subset of these schemes based on their ability to optimize for the gap measures. For that, we use 25 real-world graphs as input and use it across 11 reordering schemes, and their quality is judged by the gap measures. From this first performance chart, the takeaway is that the partition-based schemes like rabbit order, metis, which are shown in red, optimize best the average. The next result here shows RCM, which is the reverse Cuthill-McKee algorithm. This outperforms other when the objective is to optimize for graph bandwidth. RCM is the one in black. Moving on to the real-world application study, the ones we look at are community detection and influence maximization. Our choice of end application is motivated by the fact that these represent a far more advanced and complex graph operations that feature in several large scientific pipelines. Furthermore, they encapsulate two very different types of algorithms. Community detection, on one hand, represents the classic multi-level iterative graph algorithm, while influence maximization implementation entails running numerous stochastic BFSs over the graphs to collect samples. First, let us take a look at the community detection results. We present the result as a heat map where redder is better. The takeaway here is that Grappolo ordering outperforms others in general as far as the phase and iteration times are concerned. And also for parallel efficiency, Grappolo usually has the highest. This also, while having the lowest work per edge, is indicative of better load balancing. Now we take a look at the memory hierarchy boundedness. Our expectation here is that the lower memory latency should correspond to boundedness at lower cache levels, and lower iteration time should correlate to lower memory latency, but that's not the case. Grappolo ordering makes the application more DRAM bound, whereas we were expecting it to be more L1 or L2 bound. We believe that the graph traversal costs may not be the dominant factor in the algorithm's execution time. The algorithm's use of auxiliary data structure. This can result in additional memory accesses that negates the effect of ordering. We now turn our attention to influence maximization. We take a look at the memory boundedness here as well for the largest graph for which this analysis was possible, which is the splitter graph. The expectation here is that the runtime profile would be more cache bound as a result of reordering, which would reflect in the throughput and execution, but that's not the case. In summary, we see that partition-based schemes do better optimizing for average gap profile. RCM is best when we want to reduce the graph bandwidth. And reordering has more benefits when community detection is the end application than when it is influence maximization. Finally, does reordering matter? Yes, definitely. It shows us how the end application will use the memory hierarchy. But is reordering worth it? Well, if the input graph is used enough times to amortize the cost of reordering, then yes. And that brings us to the end of our presentation. Thank you.